All right, welcome everybody to today's webinar hosted by the International Solar Energy Society ISES and by the IEA SHC Solar Academy. We are very pleased to have all of you here, and we are especially happy to welcome back the IEA SHC Solar Academy for 2020. This is a special webinar coming to many of us to our home office in these very special times, and I want to give a personal welcome. Thank you everybody for joining, and I hope we're going to have a nice webinar together this afternoon. My name is Arabella, and I am the Communications and Outreach Officer here at the ISES HQ in Freiburg, Germany. And I will give you a short introduction into ISES and the work we do, as we have many new participants joining us on the webinar today. The International Solar Energy Society ISES is a non-profit UN-accredited membership NGO. Our vision is 100% renewable energy for all, used efficiently and wisely. ISES represents a diverse membership of academics, researchers, energy practitioners, consultants, students, businesses, and advocates. And ISES works together with like-minded organizations from countries all around the world to advance the renewable energy transformation. There are many benefits to joining ISES, and you can find out more on our homepage. Some of the benefits are the exclusive access to presentations and webinar recordings, such as today's in the ISES Webinar Archive. ISES members can also get discounts and even free registration to ISES events and partner events. You can always find out more info about upcoming conferences and discounts on our website, or you can also always contact us at public.relations@ises.org. Every month, ISES publishes a newsletter for our members where you can follow our progress and share your news. Members can also subscribe to our academic journal Solar Energy, which is our flagship publication at a reduced price. And in the ISES online bookshop, ISES members qualify for reduced prices on the different publications. So we welcome those who are not yet members to join today, and for those who are already a member, we thank you for your support. There is a special benefit to all attendees of today's webinar, and we are very happy to offer you a special discount when signing up as an ISES member. All attendees of this webinar today will receive a 20% discount code as a follow-up to this webinar over the next days. This special offer will only be valid for about 2 weeks after this webinar today, so sign up quickly and join ISES and the global solar community. Now for some brief information on the webinar and especially the Q&A section before we start. During today's webinar, our expert speakers will give us presentations on PVT, and for the Q&A section, we invite you to send in your questions, and we are looking forward to your participation. When sending in the questions, please write who the question is for and keep your questions short and precise. I am now happy to introduce you to our moderator for today, Bärbel Epp. Bärbel will introduce you to our speakers and also guide you through the Q&A session. Bärbel is the founder and managing director of the agency SOLRICO, Solar Market Research and International Communications, a network for solar thermal professionals worldwide. She is responsible for the international newsletter on the web portal solarthermal.org, which has been dedicated exclusively to the solar heating and cooling sector. Bärbel graduated in physics and looks back on more than 20 years of journalism in the field of solar thermal energy. Now I'm happy to hand over to you, Bärbel. Thank you for joining us, and the floor is yours.
Thank you, Arabella, for the nice introduction. I welcome everybody this afternoon and on a special day where the world is, well, a bit in trouble, and I think we are all a bit closer together because we share a lot of trouble with this corona. So I hope that everybody is fine and you're all stay and are in good health. And I'm happy to introduce you to this IEA Solar Heating and Cooling Program briefly, which is, joining ISES in regular webinars for a year, which we title under Solar Academy. So IEA Solar Heating and Cooling is one of the IEA technology collaboration programs and one of the oldest ones actually. We have 20 member countries and 4 international organizations. So you see from the colored map that we cover a lot of areas in the world. More than 400 experts from all 5 continents group in so-called research projects on a far range of topics. I have listed them here for you. It's district heating, industrial solar heat, it's industrial water management, facade integration, neighborhood planning, and compact heat storages. How can you profit from this, our office? Well, Obviously, you can join webinars, which are regularly organized together with ISES, and you find the announcement on our Solar Academy subpage. You can listen to a lot of videos that we did with experts on the different conferences on our YouTube channel, and you can join on-site trainings, which are organized in countries on request of member countries, and the last trainings were in China, South Africa, and UK. This is our website, IEA-SHC.org. You find the task which we are talking about today, also on this website. Further questions, general ones, can be addressed to the Secretariat. Please follow us on social media. We have a Twitter and a LinkedIn group, and certainly you find always updated videos on YouTube. Today's webinar is covering task 60. You know, within the IEA solar heating and cooling world, we talk about tasks if we want to say international research projects. It's a bit shorter. So today's task is PVT, PV thermal solutions for building and industry. And it's nice to have 3 speakers today. And what is a bit special about this webinar is that we have a mix of researchers and industry representatives, which gives us very different views on this technology. And it's a special thing also of this task work that always researchers and industry people or experts work closely together to find solutions or get an overview on the market. So I will give my screen now to Jean-Christophe Hadorn, and he will be the first speaker. He is the head of a consulting company in Switzerland, and he is chairing the IEA Solar Heating and Cooling task, task 60, on behalf of the Swiss Federal Office of Energy. He has long-term experiences in solar thermal energy, actually more than 40 years, and he was involved in several of these IEA solar heating and cooling research groups. He will tell us today why we should consider PVT systems. Jean-Christophe, I'm looking forward to your presentation.
Yes. Can you see it now?
Yes, perfect.
Okay, good afternoon or good evening, everyone. We're very happy to have you on board for these PVT presentations, these 3 PVT presentations. I will start with general matters and you'll see a little bit of technology. And then you will have a presentation from Laetitia, who is head of industrial company manufacturing actually PVT collectors and systems. And then you'll have some nice insight into what we are doing in task 60 about the performance indicators and how you should consider PVT together. But first of all, let me tell you why you should consider PVT systems when you're designing something. The first thing I'd like to tell you is the strength of PVT. In PVT, we can do electricity for sure. We can do also heating, direct or indirect with the heat pump, or cooling, also direct during nighttime, or indirect with the heat pump or compressor. And what we think is our strengths is that you maximize the output per area of your roof or your collector area. In some cases, you will see you get 100% solar because you can also run the pump with the PV part of the solar collectors. If you use a heat pump together with PVT, it's a nice source because you have no noise and no borehole. And if you have a borehole, you can regenerate the borehole during summertime. And of course, if the load is quite favorable, I'll show you some cases, the payback time is really impressive. Now, I'll explain a little bit what is PVT. I guess most of you know it's a hybrid technology, and we have a absorber on the bottom of the collector, and on top of it we have PV modules which is linked to the absorber by some gluing system. You can have a glass on the right hand side, you can have a glass on top of it, or you can have no glass, which is called uncovered in the common language. but for scientific people, scientists, it's called WISC collector. You will heard maybe more than one time this WISC label, which is, it stands for wind and infrared sensitive collector. If it's not glazed, you get some actions during the nighttime by the ambient air here on the top or the ambient air at the bottom of the collector if he's in a freestanding state. You see here why the Task 60 logo was designed like this. In the yellow part is what the thermal is going to convert, the light from the sun, which is going to be converted by the thermal collector, the absorber, and the blue one is what the PV cells are going to convert. So if you add the yellow and the blue spectrum, it's a larger spectrum than if you were only on the yellow or separately on the blue spectrum. It's why we get more solar energy out of a PVT module than out of each of the modules. But we have, of course, factors affecting the performance of both the PV and the T. Let me make it simplify in a simplified version here. We have one effect on the what we call tau alpha, the transmittance and the absorbance of the collector, which reduce a little bit the thermal efficiency. We have also what we call number 2, the heat removal factor, which is the way the heat is moved from the PV cell, which is the absorber, down to the metal sheet and down to the fluid. It's a little less than a normal thermal collector, so you get a negative effect also on that. And the third effect, which is now for the PV cell and PV module itself, number 3, if you have a higher temperature below the PV cell, you all know that most of the cells are going to perform a little bit worse. But on the other hand, if you have a lower temperature, and this is what we can achieve with the PVT in some cases, mainly with heat pump, then you get a little bit more efficiency than without. Let's see that on this kind of comparison. On the left-hand side, you have 29 square meters of thermal and 13 square meters of PV. And the right-hand side, we compare that to 42 square meters of a PVT collector. Then the heat would be about the same, 22 megawatt hours for the separate case, and 22 also for the other case, because we have less performance. We have more square meters, but a little bit less performance. You see the 759 compared to the 544 kilowatt hour per square meter we get from the T part. Electricity will be much higher because we get 42 square meters of PV without any noticeable reduction compared to 13 square meters. So all in all, if you add all the energies, you'll see that we get 13% more from the same roof area. And also notice that on the right-hand side for PVT, the electricity to heat ratio in this particular example is 1 to 3.8. I'll come to that in a moment on the diagram to make you have this figure in mind, the relationship between electricity and heat in a PVT collector. Now we look at the cost problem. I go straight forward into it because I'm sure that you'll have many questions on that. If you have standalone components, the current status of cost, it's a medium cost, average cost over Europe, I would say. A thermal collector glaze is about 250 euros per square meter, and a PV is about 114 euros per square meter. If you add this up, it's 364. So if a hybrid system, PVT, would have the same productivity or the same value of energy, roughly compared to the yellow part, then the PVT glazed collector, I take a glazed example here, should not cost more than 364, and you save a little bit on components during the installation and also in time during the installation, so maybe like 50 euros. So all in all, is the PVT collector glazed able to be to cost less than 414 euros per square meter? If the answer is yes, you better go PVT. And I can tell you the answer is nowadays, in some countries, really yes. So PVT might be really cost competitive. I'll give you some examples. You'll see more from Laetitia's presentation. You see here on the top a glazed collector with PV on top, and you recognize the absorber and the piping. But what is strange for solar experts, you see piping and wires. This is typical of PVT, sorry for that. On the left-hand side, there is a very nice collector in evacuated tube collector combined PVT, which goes to high temperature, more than 150 degrees Celsius can reach. And on the right-hand side, it's an uncovered collector, aluminum absorber, and then glued on it a traditional monocrystalline or polycrystalline module. Other examples you see here, nice examples from unglazed collector. You'll have lots of presentation afterwards on nice project with this. You see it's very thin, very integrated into the plan of the roof. And on the right-hand side, one of the best seller in France is the air collector, is a PVT air collector, which is a combination of an air collector and PV on top of it from a nice French company here. But in the world, there is also researchers and engineers working on concentration and concentration collector. You see one example here, very nice example, with a very high efficiency PV cells, little cells you put on the concentration, the line of the trough, so you get like maybe a 50 up to 100 concentration factor, so you can pay for very nice and efficient solar cells and have a combination of heat and power. Here you see the ratio in the yellow circle, 1 to 1.5, because we are at high temperature. And let me come to those curves that most of the solar people know very well. In black, it's a flat plate collector standard, and in green, it's a flat plate collector, but PVT, so with a cover. You see, we have this little, about 10% up to 20% less efficiency in this particular example. Concentration is the blue line, and the whisk collector, the uncover, is the red line, which you all know from the thermal science, thermal collector science. I dotted also that the efficiency can go up to more than 1 on the left-hand side, because the efficiency is defined with solar radiation, and with the whisk collector, we get more than solar radiation with ambient energy. And you see in the dotted black or dark blue, the PV module is a little bit affected by temperature. So the efficiency is not quite constant, starting maybe here from 14% down to 11%. And something you can notice and is interesting to know for PVT collectors, it is this. If you look at only the PV module plus the thermal part, the PVT, and you'll find the red arrow, let's take the one in the middle, the ratio between what the PV is producing to what the T is producing is 1 to 3.8, what I said previously. It means that the collector is mainly operating at about 45 degrees Celsius, as you can see. And the more you go on the left-hand side, the less temperature the collector will operate, and then the more the ratio will be high. And then when you move on the right-hand side, then you have a 1:1 ratio. So when you look at this ratio, you can have a real good idea on what was the operating temperature, the mean operating temperature of the PVT module. If the ratio is high, it's a low temperature PVT module operated. If the ratio is about the same, it's at high temperature that it happens. So now you see the applications are quite straightforward. If you have the 3 collectors like uncovered, whisk, covered, and concentrating, depending on the temperature of the application, you get applications where the heat pump can be coupled with uncovered collector, so to say. And then you move to, of course, what you all know from thermal, swimming pools, very interesting load to supply with solar, the domestic hot water, then the space heating, and on top of it, you have agriculture like drying and greenhouses, and to the right-hand side, all the processes, the heatful processes can be full field up to 120, up to 130 with the evacuated tube collector. So we have the right a wide range of applications with this PVT technology. I show you a few examples. You get more from Laetitia. This is very famous in France. Very well insulated houses can be heated by air, with air if you want, the air heating system. And then you have PVT, air PVT collectors on top, producing in the ratio of 1 to 3.3, as I noticed here. So it is about 40 to 50 degrees Celsius, as you remember my explanations. And this is the bulk of the French market nowadays, because it has been developed since 8 years, and the low energy houses are keen to use that and get like 50% solar fraction with 20 square meters on the roof. Another example comes from Spain here. It's a fireman house where they have a high domestic hot water load. It's a 28 PVT panels. A PVT panel is quite high, it's quite heavy when it's glazed, like 46 kilos in this example. It's much less when it's not glazed. We have in that example 43 square meters, you can read, and 7.28 kilowatts. And the production is quite high. Thermal, that is measured production, 718 per square meters. That is in Zaragoza, so it's a nice climate. About 50% efficiency, year efficiency, a little bit less maybe. And the electricity is like also really interesting, 1,320 kilowatt hour per kilowatt peak. And the ratio heat to electricity is 1 to 3.2, or electricity to heat. So you see it's operating for DHW around 40 degrees Celsius. It's 66 solar fraction for this installation in this fireman house. We have also coupled PVT coupled with ground source heat pump, and I can show you these examples. It's 100 flats in Switzerland. There are 28 boreholes of 200 meters and 1,300 square meters of PVT, uncovered PVT. And the performance after the first year of operation was such that the yield was 330 for the thermal, which is quite good, and the electrical was 163, which is quite normal. And the PVT collectors unglazed are used to regenerate the boreholes, because we got 28 boreholes over the land, and they are quite close together. So you need to recharge a little bit the storage, so to say, during the summertime. And maybe the last example I would like to show you today is large industrial projects that like those ones can also be favored with PVT. You can operate big greenhouses like this, which are needing solar hot water, and also some heat in the foot of the plant, sometimes in the ground, buried pipes in the ground. And also they need big fans to move the air inside the greenhouse. That this could be achieved, and that can be achieved with the PV part of the PVT. There are big realization in Israel and in China, up to 1 megawatt with this PVT system. A bit on the market, just to have you understand that the uncovered water collector, the WIS collector, is dominating the market. Some covered collector are fighting against that and taking over. Probably in the long run it will be half-half, but it's you see it's more than it's about 75%, 3/4 of the market with these two collectors, and the rest is distributed as you see. We think we have now 2 million square meters installed PVT in the world. We have a survey saying 2 years ago 1.1, and since probably there has been some growth, we think we have 2 million square meters. It's not that much. Maybe you know the thermal collectors, 180 million square meters in the world. So we have like less than 1% or about 1%, but it's growing probably faster than the thermal collectors. We have lots of industries involved in Task 60. I listed here some of them. and you can reread that in the final presentation you will have on the ISES website. But we are very happy to have many manufacturers coming into the task and discussing with researchers trying to do better and better applications, products, and systems. The best applications for the return on investment are found in the 8 sectors I sketched here, and the characteristics of those sectors in the thermal part is that we have a high domestic hot water demand with a very low seasonality, so you get a high demand all over the year. And the second, which is very favorable for PV and PVT, is that there is either a high feed-in tariff or one feed-in tariff, or more interesting, you have a lots of self-consumption of this electricity, and then you substitute maybe a high electricity cost with the PVT module. So for hotels, for example, you get nice payback time. I show you an example just after this slide, but we can reach 4 to 8 years for DHW in hotels in latitudes of the big sun belt over the world. And you see other examples with whisk collector uncovered and heat pump from Laetitia right after me. I show you this case, which is really symptomatic of what we can achieve with PVT in good climate, like Barcelona. Say we have a 200 rooms hotel. We put 200 PVT modules. That means 314 square meters for 56 kilowatt peak PV. And with an annual demand, which is quite high, more than 800 megawatt hours, the solar fraction can be 34% of this hotel. And the T is operating with a 50% efficiency. You see the high efficiency and the high yield we get in Barcelona. And the PV is also quite high, and there is 80% self-consumption in this case in the hotel. The investment, total investment for the case, that is the collectors and the installation and everything in the boiler room, was 730 euros per square meter. So the payback time, if you do the division, is 4 years. You see this in the bottom. You have 4.5 years to finance, so to say, in red. And then afterwards, all the green part is the present value of the money that the owner of the hotel is getting back. So if the lifetime is 25 years, he will get like more than 1,800,000 francs back from this installation. So it's a very interesting investment. We have been doing quite a lot of work in the task 60. It's still on. We have 1 year to go on still, but we have issued a few reports you could surely get soon on our website. I noticed here, show you a few of them. And we have also opened a Wikipedia page very short time ago. You can go and see what we think about PVT systems and applications on this new PVT Wikipedia page. I will conclude with discussing a little bit very rapidly the challenges we're facing with PVT. As I said, industry is there, so we have reliable product. Models, simulation, and prediction, it's now done. We've been integrating the nice equations for all kinds of collectors in most of the simulation models, but we are challenged on a few aspects like awareness. I guess PVT is not well known in the solar community, in the PV community, in the installers community, and also by the architects. We are working on testing T and PV together with the organisms you can see here, so we can have a common and very reliable standard, which is now on foot. We have to see the temperature influences on the long time durability of the collector, as you might imagine. We have a few years experience, but that's not enough. We have labels and certificates, one from Solar Keymark, which is now ready, and a few other aspects like investments and total cost of ownership. As you have seen, we have good examples, but we need more. Optimization is quite tricky because it's a very multi-variables environment. You have electricity and heat. You can store the heat in cold storage, hot storage. You can store the electricity in batteries or not, etc., etc. We have to gather best practices and make case studies. We have a nice report about 26 case studies already studied into a report of task 60. And we have KPIs to set up for a fair comparison, because it's not that you can add electricity kilowatt hours with thermal kilowatt hours. So we need some more on that. And you'll have a nice presentation from Daniel right after Laetitia. Of course, if you are interested in architecture, you would like to have nice BI, building integrated PVT solutions. I guess some are on the way, but still there is a lot of improvement and innovation you can imagine on this topic. And to conclude, I would say a very simple message. If you consider PV for a project, let's try to consider PVT also before you make the choice, please. If you need solar domestic or water for a client, for example, why not PVT? Try to have it in comparison. And if you think to switch to heat pump from any kind of heating system, think before air and boreholes, or with those, think PVT, because it's a nice source also for heat pumps. And this concludes my presentation. And I thank you very much. You have all the links here, Wikipedia, our Task 60 link, and the LinkedIn group we have. And I'm happy to give the floor back to Bärbel, I think.
Yes, absolutely, Jean-Christophe. Thank you very much. I think this was a great overview, and it happened to have nice economic figures included, as well as demonstration and technology photos. Thank you very much. There are already a lot of questions, but please patient yourself a bit. We will have enough time for a long Q&A session at the end. So I would like to introduce our second speaker. It's Dr. Laetitia Brottier. She is co-founder and innovation director of the French company Zenhäusern. It's a company that was founded 2010 to develop, industrialize, and commercialize PVT solutions. As an industry player, the company was very active in Task 60 and supported the researchers in their doing. She will give us an overview of the PVT industry and perspectives. Laetitia, I'm looking forward to your presentation.
Thank you, Bärbel. So as proposed, I will give you an overview about the PVT industry and perspectives. Just a word about Zenhäusern. We are a PVT manufacturer since 2010. We already have more than 1,100 installations over the world. And we have a very good growth, as we have 5 times the turnover we had 3 years ago. We already have launched 3 versions of PVT modules and won 17 trophies of best product over the world. We are our production and innovation are made in France. So what about PVT? Why consider PVT? You already know the photovoltaic market and the solar thermal market. Both markets are already big markets, as around 500 gigawatts have been already installed as total capacity. But if you look carefully about prices, for example, in the utility scale, you will find that PV is around, as an average, 85 euro per megawatt hour, and the solar thermal for district heating is around 40 euro per megawatt hour. So solar thermal is cheaper. It's a cheaper solar solution for heating than PV is. Again, about in a residential scale, you will have around 130 euro per megawatt hour in France, to be compared for residential domestic hot water with solar thermal to 80 euro per megawatt hour. So both solutions are has very low carbon impact, but solar thermal is the cheapest solution for heating. But you all know, I think, that the photovoltaic market is more profitable because the electricity is more expensive. and this is also a fast-growing market. It grows faster than the solar thermal market. But why not consider PVT as a profitable electricity solution, and also in the same time a cheap solution for heating? Why is it interesting to consider electricity and heat in the same time? Because building and construction represent around 309% of the energy-related carbon dioxide emissions. So the World Green Building Council have launched a coordinating action toward 100% net zero carbon building by 2050. We already have in France, for example, the label positive energy and carbon reduction since last year. And we have a double constraint. We have a constraint in energy consumption that should be low, but also in the life cycle analysis of the building, we need to respect a low greenhouse gases emission. And if you try to do this, for example, we try to do it in the Edge 2020 project called ISES. We try to build some positive energy building and also to have a refurbishment for buildings into positive energy building. And the solution to achieve this goal was to use PVT with the ground source heat pump. That's really what Martin Bouygues also told us. It is his testimony here. Bouygues Construction is one of the biggest building company in France. And he says, one thing is certain, we will always need to produce domestic hot water, and the space in our building rooftop is not infinite. So the two-in-one technology, that means the PVT technology that combines two essential energy needs of building today and tomorrow, is very efficient. And he tried to use this technology for its own building and observe its excellent performance every day. About prices, you all know that the PVT has a very quick learning curve. Maybe you don't know that the solar thermal also has a very quick learning curve. That's because PV double its total installed capacity quicker than the solar thermal do. And but I think really that PVT is an opportunity for solar thermal to benefit from the quick reduction in PV cost. But just be careful, because the clients expect to see the same percentage in price reduction for PVT than they have with PV. So it's really a challenge for the industry, as the selling volume is really not the same in PVT than in PV. We are speaking about PVT, but Jean-Christophe have already shown us that PVT is has a lot of variation. We have variations in design in all layers. You can see here just proposal layers you can find in PVT, and you can see that in the front face you can change the insulation. You have the WISC, the uncovered PVT. That WISC means wind and infrared sensitive solar collector. But you can have also overglazed PVT, vacuum tube PVT. And for the PV, it's the same. You can choose many cells. For the fluid, you can choose water, air, and other fluids. And for the heat exchanger, you have different material, geometry, the contact in between the heat exchanger, the PV module can vary, and also the fixation can be glue, encapsulation, mechanical fixing, and also for the back face insulation, you can also choose to not have any insulation or to have a rear insulation. And all this wide diversity in PVT concepts are already in the market. You can see here a vacuum tube example, a concentrated PVT on tracker or without tracking, an air-based overglazed PVT collector. And even for WISC PVT, we will see just after that the WISC PVT, the uncovered PVT, are the most common collectors. You have a lot of materials used, for example, stainless steel, polymer, copper, aluminium, and with aluminium, you have a large diversity in design. You can find serpentines, wall bond, extruded aluminium. But what we have a good news for this waste collector. We already have the norm, the quality norm, to qualify the collectors. Since 2013, the Solar Academy clearly identified how to approve a flat pay PVT. You have to repass for the whole PVT module, the IEC for photovoltaic quality, even if your PV laminate is already certified. And also you have to pass the ISO for the solar thermal quality with the old PVT module, and you to do the performance testing with the photovoltaic running in MPP mode. That means in a maximum power point of the electricity part. Just a warning here, the aging cycle you have to pass when you pass the IEC is the same as the one you pass for a normal PV module. So you go up to the 85 degree. So if your PVT externation is over 85 degree, you have not the guarantee with the certification that the PV part of the PVT stands cycle above 85 degree at the your stagnation temperature with no degradation of the PV performance. You need more information from your manufacturer. About manufacturer, I give you here bubbles. The bubble in the left part, you have a number of manufacturers per country. The area of the bubble is proportional to the number of manufacturers, and you can see that we have some manufacturers in the USA, China, Israel, and Australia, but most of the manufacturers are European. And if you look at the market in Europe, only in Europe, for water PVT, you will see that where you have some markets, you have a manufacturer. That's mainly because each manufacturer still mainly sells in its domestic market. I split the market numbers per country and also per design. You can see that in the yellow box and in the blue box, you have whisk PVT collectors, water whisk and air whisk PVT collector. You can see that only in France we have a large, big market in air PVT. But if you exclude France from the panorama, from all the markets, you can really see that the whisk water PVT is largely dominated the market, much more than the glazed and the vacuum tube and concentrated for at the moment. That could change maybe. We have a wide typology of clients because we can provide PVT for individual homes, multi-house owners, social housing owner, but also for health, sports, tourism. So the clients to address are very large, and also the system that we can consider are very different. We can go directly to preheat solar domestic hot water or pool, for example, but we can go also through a heat pump. We have three types of heat pump connection. We can go directly with the glycol to the heat pump, or we can have a storage in a tank or a storage to the ground. And it really depends on the project. So we have we are very more complex, I think, than PV because of this solar thermal part, and that's maybe why we have a barrier in the market today. We really have an unfair supports for PVT yet. For example, when you produce exactly the same as a PV plus solar thermal, I took here something classical in France, 6,000 kilowatt hour per year in electricity plus 1,500 kilowatt hour of thermal energy per year. You can really have more support with PV plus solar thermal side by side that with PVT. And this is due to unfavorable criteria for PVT. I think even if we have qualified professional to install PVT, we still have less of a professional or skilled people in the administration that knows really PVT. For example, we are asked for the power of the PVT, but at high temperature, sometimes we don't know we don't go at high temperature, so it's not interesting to ask for this power. We have asked for a minimum of kilowatt hour per square meter, even if we can have a large area of PVT in the roof without any problem, because we have the PV to put anyway. Also for the energy labeling, the energy labeling is calculating at 40 degrees above the ambient. That's not for PVT, that's for sure, at least for with PVT. And also sometimes PVT is simply excluded of the support. So that's really a problem for the PVT market to grow as quick as they could grow if we could have a fair support. So just to sum up, the strengths and the opportunity the PVT has. PVT is already competitive. That was I've shown Jean-Christophe already. It's already competitive in comparison with PV. We already have a lot of manufacturers, more than 55 manufacturers in the market. The norms are already in place. We have thousands of successful PVT installation already running. But as weaknesses, we have lack of awareness for prescriber, maybe because we still are a young technology. We are more complex than PV, and that's maybe explain why we still have unfair public supports at the moment. But we have opportunities. We can, as PVT, we can take advantage of PV cost. PVT is really an interesting solution for positive energy building and low carbon buildings. We already have many plumbers already qualified in solar heating. That's good news for us. We need them. They can deal with the complexity. And we have seen that we can have synergies with heat pumps. As a threat, as all renewable energy, we fear the fossil prices. We need high fossil prices to be interesting. And PVT is asked sometimes to follow the rhythm of the PV price reduction. That could be an issue. And if we have the success we hope, and we become a fast-growing market, in Europe we will have the difficulty, as always, to finance massive investment for industry, for industrial companies. I think it's specific to Europe. And but I think we can easily tackle this threat. If we have a booming market, maybe we can have an emergence of poor quality, but we already have norms and we already have qualifications for plumbers, so it's maybe not a big issue. So about PVT, what I remember is we have the norms, we have the plumbers qualified, we can take advantage of the PV cost. So my conclusion will be, let's go to PVT. Thank you.
Thank you, Laetitia. Thank you. This was an interesting perspective from industry point of view, also looking in some of the market barriers that appear on the administration and funding side. Thank you very much for that. We come now to the third and last speaker, but be confirmed that all the presentations and the recording will be available afterwards online. I think we have some people worrying about bad audio connections and maybe too fast presentations and so on. So please be confirmed that all will be available afterwards for rechecking and even for listening again. So our last speaker is Daniel Zenhäusern. He's also from Switzerland. He's a scientist and project leader at the SPF Institute for Solar Technology Rapperswil since 2012, with a special focus on PVT. One of his current fields of research is the development of highly efficient covered PVT collectors. And he will talk about key performance indicators of PVT systems. So Daniel, your presentation, please.
Yes, hello everyone. I hope you can see my presentation. Yes?
Yes, works perfect.
Perfect, I'm sorry. Okay, thank you, Bärbel, for the nice introduction. Thank you everybody for listening and for the opportunity to speak here. I will start with a brief introduction, and then I will rather quickly move on to two examples where key performance indicators are applied to PVT systems. The two examples are, one is the comparison of 3 systems in Switzerland, solar heat pump systems, and the second example will be the comparison of a number of systems that we have collected within task 60. Okay, so what is actually the purpose of a key performance indicator? In short, we want to have such indicators to be able to compare a PVT system or part of it with its rated, expected, or optimal performance. Say we have an idea from planning what the performance of a system should be. The indicator should help us to see if this fulfills expectations, or also, for instance, if we do optimizations in a system, see if the optimization are fruitful. Second option is we want to compare the system to a different system, another PVT system, can also be systems of other technologies, etc. Obviously, values that flow into KPIs can come from measurement data or equally from simulations. Now, in task 60, we thought about what indicators could be helpful for PVT systems. The idea was not to introduce a number of new ones or as many new ones as possible, but we wanted to also use obviously those that already are used in other domains. But yeah, so a big list came together of possible indicators, and of which I will give you here just a selection, so to say, the key performance indicators. And we have split them into 3 categories. We want to be able to say something about energetic performance of a system, about economic performance, and also about environmental impact. So in the energy category, we have, we think the most important will be these. First one is thermal and electrical solar yield per square meter. That doesn't need more explanation. Second would be thermal and electrical utilization ratio. Here the yield is divided by the irradiation. So that is helpful to compare systems that have different irradiation sums, are at different places, etc. Have a more fair comparison there. Third, we want to have an indicator that tells us about the quality of the heat. And there we want to know something about its temperature. We would suggest to use the so-called power-weighted collector temperature. This is a weighted average of the collector temperature, weighted with the thermal output. Then further, we want to say, well, we think it's important to also give, if possible, solar thermal and electrical fractions. That's how much of heat or electricity demand of a system can be covered by the solar installation. And then here, a particular thing for heat pump systems is the seasonal performance factor, which there is very handy to compare different systems. So these 5 are for comparison of solar systems, and these for heat pump systems. Now in the economic category, First one is specific investment cost per square meter. We've already heard that in Jean-Christophe's talk. Some numbers on this. That's often easily available. Then the levelized costs of heat and electricity, that's something used broadly in many domains. So we also want to be able to give our numbers and compare them. And then in the end, what's also nice, if you want to compare a system with PVT to another system, it's nice to know how much fuel or grid electricity costs maybe you saved compared to a fossil system or the like. Then again, if you want, especially if you want to compare to other technologies or fossil powered systems, it's interesting to also be able to give numbers on how much primary energy depletion you avoided, or how much global warming impact you avoided. Now, with this, I would like to, we would like to add that we have there's a lot more details to say on this. Many of these indicators come in different variants. You have to specify system boundaries, etc. So all this stuff, I'm not gonna go into it in detail, but you can read up in a report. Reports that will come out from in spring on our webpage, Task 60 webpage. We also have a nomenclature defined there, which we think we would like to encourage people to use. The second report is about this comparison of 24 systems, of which later on I will show a little extract. But before coming to that, I want to take example one. Example one is a building complex named Socha in Switzerland. There we have the situation of that we have three buildings that we look at. So that's building A, B, and C. All are built exactly the same, orientation almost the same, but they are different in that they have different solar energy systems. A has a PV plant plus a battery storage. B has a PVT plant, and C has a combination of PV and flat plate thermal collectors. All systems have a heat pump that is coupled to 5 boreholes for each. And then in B and C, I have to say, solar heat is used for borehole regeneration, domestic hot water, and space heating. The basis for the comparison, as a basis, I give you the energy balance. On this plot, you can see what goes into the system, what energy goes in, and what output it gives. So you have systems A, B, C. What goes in is grid electricity, PV electricity, ground heat, and in 2 of the cases also solar heat. And what goes out is heat for space heating, hot water, and not related to the heating system, but still that's a useful output, is PV that goes to the households and PV that goes to the grid. Here you can already see, even though the buildings are exactly the same, consumptions are different. So this you should bear in mind when you put them, when you compare them. Okay, first aspect to look at is the solar yields. In yellow, you have the irradiation on the roof. So for each roof, that's the same. And then what comes out in solar energy, in terms of solar energy. So in blue, you have the electricity, which is higher in A and B because they have larger PV active surface. And B and C have thermal output also, which A doesn't have. Now, the first indicator I mentioned before is this, well, one of the indicators I mentioned is this quality of the heat, namely the power-weighted collector temperature. So here, for both systems, like uncovered PVT and flat plate thermal collectors, in both cases, we have similar temperature. The amount of heat is almost the same, but bear in mind that in the case of PVT, the surface area is much bigger. So from this, we can calculate the solar utilization ratios. So that is something that is well known. We divide the yield of a component by its surface area, like electricity yield of PV divided by PV surface area, or the same for the thermal components. There we have the electrical utilization ratio. It is similar in all cases. PV panels operate more or less at the same efficiency. Thermal utilization ratio is higher in the case of the thermal collectors than in the case of the uncovered PVT collectors. Now, what we think is an important improvement, or what's also an interesting quantity to look at, is the solar utilization ratio related not to the component surface area, but to the solar installation surface area, or to, let's say, the roof surface area. If you do that, then the picture changes, obviously. Here, still, a building A has no thermal utilization ratio, so none of the radiation on roof A is transformed to thermal output, to useful thermal output. Building B and C, you have useful thermal output here. Electrical utilization ratio is about the same in building A and B. You have the same PV active area, and building C, the roof brings less electricity. And if you count the two together, and that's where PVT shows its strength is most obvious, is if you sum, you can question that, but if you sum electrical yield and thermal yield and divide it by the irradiation, then we would speak about the energetic utilization ratio, and there PVT is clearly winning, and actually by 33% over PV plus T. Another interesting indicator in the case of a solar and heat pump system, as we have here, is the seasonal performance factor. So one way to form this is to just look at the heat pump, like divide the heat that heat pump provides by the electricity it consumes. Here, all the systems have similar values. B and C are a bit higher. This can be is possibly due to somewhat higher source temperatures, and in the future, where these two have borehole regeneration and building A does not, this difference could be even higher, so that B and C will be higher in the long run. Now, if you want to look at the whole system, not only at the heat pump, you can look at, enlarge the system boundaries. So you will divide the useful heat the system provides to the user by all electricity that the system consumes, so including circulation pumps, etc. So there we get the following numbers. They're obviously lower because you have losses, etc., more electricity consumption. Here you have this hierarchy that B and C are better than A. B is better and C is better because, well, they get the better, the more thermal energy they bring into the heat storage directly. So that's the advantage here. In this picture, you do not include the fact that actually the system produces electricity for itself. If you want to take that into account, we suggest to use the seasonal performance factor grid instead of total, where we only consider what's taken, like electricity that's taken from the grid. So we reduce, so we subtract from the electricity consumption the self-consumed PV electricity. So here the picture again changes very much. Here B and A get this benefit that they have more PV production, and of which they also can use more themselves. A has here the big benefit of having a battery, or let's say this is what makes A better than B mainly. So these are the things I just said, and there's a lot more to say on this SOCHA systems, and I would like to refer you to a future final report. Should be published this spring, and you will be able to find it on our webpage, spf.ch. Now I want to move on to the second example of application of key performance indicators. it is these 24 systems that Jean-Christophe Hadorn has mentioned that were collected in task 60. So many countries, like the systems in many countries, as you can see, many different applications, domestic hot water and space heating, pool heating, ground source coupled systems, etc. We have different systems with varying collector types, covered, uncovered, concentrators, one evacuated tube, and also quite a range of different collector field areas ranging from a few square meters to 600 and more square meters. Here I also want to look first at the utilization ratios. Here thermal in orange and electrical utilization ratio in blue. They're categorized by different heat uses. Here you can see that we have quite a spread, so a lot, very varying utilization ratios. Some of this spread is explained by different locations, different climates, etc. And also by the fact that some systems might need more optimization, some are pilot systems, etc. But still, if we take the average, we can see more than 25% thermal utilization ratio with, as I said, a large spread and about 12 or so percent electrical utilization ratio. As I said, conditions of operation have an influence on these values, obviously. And if you take only the uncovered collectors, the system with uncovered collectors, and plot the thermal utilization ratio as a function of the collector operating temperature, this other KPI, then we see, as one can expect, rather clear trend that, as you would expect, with higher operating temperatures, you have a lower utilization ratio, so that is consistent with expectation. Now I would like to come to a financial KPI, that is this specific investment cost per square meter. Here you can see there are already fewer points. We don't have the numbers of all the systems, so I only plot those that were available. And also here you can see, well, one thing you can observe is that we have not maybe probably due to the low statistics, not a clear trend that this would decrease with the collector field size. But yeah, this will be with more statistics is very much expected. And what you also can see here is that we have very high spread between roughly 400 and more than 1,600 euros per square meter. But the message here maybe to keep is, or to the good news is that we really have values that are low, like that are around 400. That's a commercial system, which goes in the order of magnitude that Mr. Hadorn mentioned before, of 360 euros per square meter, where things would be cost competitive. I think also in other cases things can be cost competitive because yeah, this is matter of context of very often. Let's go on to the next indicator here, levelized costs of heat and electricity. There are just some background. Counted are only the costs of the solar energy system, all components, but not the backup system. We attribute in the costs to the heat system by 2/3 and electricity system by 1/3. That's a bit of a open question in the case of PVT. How do you attribute costs? Yearly maintenance costs are taken to be 1% of the investment cost, system lifetime 25 years, and real discount rate is 3%. And with these assumptions, we get the following picture, where here I don't say which system is which, but you can see an idea of what values can be achieved. Again, you have a high spread, but I should mention again that many of the systems are pilot systems, so this can be a reason for that. But what again you can see here is it is possible to get pretty low values, around 7 euro cents for the kilowatt hour of heat, and around 11-12 euro cents per kilowatt hour of electricity, which can be very competitive values. With this, I want to close and thank you for your attention with a picture of my home office surrounded by solar plants, not PVT, unfortunately.
Okay, thank you, Danielle, for this interesting presentation on KPIs. Well, I have a couple of questions, and I will start straight away. We have about 20 minutes left, which is good news. Jean-Christophe, first of all, somebody wants to know whether there is a list of PVT producers available. And the second question was regarding the 8% evacuated tube collectors that was seen in your pie chart when you showed the different technologies and their presence on the market. And the person wants to know that he only knows Virtu from Naked Energy and which other might be included in this 8%.
I'll try to answer the first question about the list of manufacturers. We don't have a complete list of manufacturers in the world because there's no association of PVT manufacturers. We try to have one in the task 60, but it's not complete. I guess this is a job we could try to handle before the end of the year, having this kind of list. Maybe Laetitia, you have something which is better than everyone else?
I know many manufacturers, but I don't think we have an official list anywhere.
No, I don't think so. Maybe Solar Key Mark along the time we'll have it, because the good manufacturers are going to ask for a Solar Key Mark. So I cannot say we have the list now. Probably we have 50% of the manufacturer, but the big ones, the one appearing on the statistics we have, because we have been collecting the statistics directly from those manufacturers. And about the evacuated collectors, there are others like Solaris, who did operate for a few years, but it didn't do many installations. And I guess we can find some Chinese and Koreans having evacuated tube collectors with PV, but not very well known. I guess this is what comes from into the statistics we showed.
Thank you. There was a question from Robert Fisher asking, how do you manage with the thermal side in single-family houses? He looked into your slide with the roofs where you compared the production of heat and PV, and he said 22 megawatt hours sounds too much for a normal house unless you go into heating. So is PVT sometimes limited that you have not enough heating demand in the building you are using the PVT with?
No, the 22 megawatt hour was certainly for domestic hot water and space heating. Of course, was for the two. In that particular case, that was just an example. You know, you can imagine many different examples. This one was done on a real basis, but you can imagine many different cases. It's the difficulty also of PVT. It's much more complex. You know, calculation with PV, you can do that on the back of the envelope, of an envelope. PVT, as you've seen with the KPIs, you have lots of things interacting. So given the solar fraction of a PVT solution is even a difficulty. So we're trying in task 60 to give the tools and the ways to have it as simple as possible. But it's not yet completely in the practice. So this is a job for the future years, probably, for the whole solar community.
Thank you. Yeah, I think that's a big issue with PVT as two productions and two technologies come together. Let
me make a point about the cost, because I showed the comparison with PV separate with T and PVT. In my comparison, it was only for the collectors, not for the whole of the installation. So when I said less than 414 or 16 euros per square meters, that was just the collector loop. Not the storage, not the heat exchanger, not the inverters, not everything. It was only comparing the collectors. While what you saw in Daniel's presentation was the global investment for the global installation, euros per square meters. That makes lots of difference.
Okay, I think that's an important point, yes. There's one technical question. I think people worry a lot about this cooling effect on PVT modules. Maybe, Jean-Christophe, you comment again on that. Somebody said that the best PVT modules average at around 0.35% per degree. So is there a new coefficient if it's used as a PVT module for the PV modules, or it's not?
No, this what we call the temperature coefficient, the K value, is negative for silicon cells, can be positive for other kind of cells, you might know, but the most cells we're using are silicon, so it's negative. So the higher the temperature, the lower the efficiency. But if you have a PV solution on your roof integrated, average temperature, working temperature is like 45 to 50 degrees Celsius in mid-Europe, because it's insulated in the back and so forth. Then if you use it with an absorber, maybe linked to a heat pump, for example, or even domestic hot water, you can operate, as you've seen in the slide of Daniel, you can operate at 36 average temperature per year. So it's less than the PV alone. So you get more energy than PV alone, but it's marginal. Many people tend to talk about this very much, with cooling effect on the PVT and so forth. We don't say this. It's a 5%, in the best case 10%. It's almost negligible. So I would not argue that PVT is so nice because you cool down the PV and you get more. You get sometimes a little bit more. That's not the main argument.
Okay, thanks for making this clear. Laetitia, more from the practical side, you as a manufacturer, some of our participants worried about having installers, qualified installers to do PVT, you know, because either you have a plumber who is on the T side or you have an electrical person who's on the PV side. What are your experiences with that?
In France, we have no problem, at least, because we most of our companies have both plumbers and electricians in the same company. But if you don't have, you can subcontract the part you cannot do by yourself. So I think really you have to install if you are qualified. If you are not, you cannot install correctly the PVT. So you need both, that's true. But the qualification already exists, so you can find people easily, normally.
Thank you. There's another interesting question, actually. Somebody said there are so many different layouts and constructions of PVT modules. Do you see personally any, well, more promising technologies for the near future than others?
That's easy for Dwalsen to answer. The Dwalsen design is the most promising design, but we use a polymer heat exchanger, for example. That's unusual in the PVT market. We like this material because it's a cheap material and it's really fit to the temperature of PVT. That's why we decide to go through to polymer. But we see in the market that at the moment the whisk design have more share. So we continue doing whisk at the moment to answer to the market simply.
Okay. An easy question: is PVT does it need cleaning?
You can clean if you want, because you at least in Europe, I don't think you really need to do. You will earn some percent, maybe 2-5%. But if you are in a very dusty place, you will need. That's really like PV. Just clean as you clean your PV in your country.
Okay. There was one particular question to your presentation referring to slide 7, where you showed the learning curves. Somebody wanted to know again how to interpret this learning curve and asked the poor PV systems was 24% down in 4 decades. Does it mean that it's each time its cumulated production doubled, the price went down by 24%? Can you explain this a bit in detail?
Yeah, the curve I shown, actually you have a function between system prices in function of the total capacity installed, and each time you double the capacity, I don't think I spoke about 24%, but more 16% for PV. So the price go down from 16% each time you double the capacity. That's true.
Okay. And the last question for you regarding your technologies. Fernando Gomez wants to know, how is the performance experience in terms of thermal stability and electrical generation with the PVT polymer modules?
Oh, but polymer. We had to invent with the TUV in Germany a new aging cycle, because polymer is very sensitive in the same time, sensitive in temperature and in pressure. So you have to age the polymer in both conditions in the same time, with pressure and with temperature. So we proved that the polymer is very stable in the temperature range of the PVT, and we have the polymer modules for more than 5 years now with no problem.
Okay. Danielle, I think there are several participants who wants to know which simulation tool to be recommended for using PVT, you know, to simulate demand and supply sides.
Yes, I can also say we do use Polyson and Transys most often for dimensioning PVT systems, but I'm sure you can also do use other things like Simulink, etc. So, but that's the two we're familiar with.
You're familiar with, okay. Simulation tools, yes. I think there is one question. The most important challenge should be concentrating on researchers to make PVT more demanded in the solar market. And there was one question relinked to that, saying that PV manufacturers at the beginning of PVT really were very much into that and developed a lot of products, but they have lost interest a lot. Can one of you explain why this trend was, that PV manufacturers lost interest in PVT?
Yeah, so I can think probably they had to focus on their core business. I'll let Jean-Christophe continue this argument.
It's what I would have said, Daniel. Of course, PV was a booming market, and they made a lot of profit just issuing the PV outside and letting the installers do the job. With PVT, the manufacturer, and I'm sure Laetitia can back up this, manufacturer must always stand behind the installers, the engineers, because it's a new technology and it's more complex. So PVT manufacturers, they want to get rid of that consulting part most of the time. And since they do good business with PV, they were forgetting about PVT. I'm sure it might change in the future.
It might change again. Okay, Laetitia, you want to comment on that?
Just to add that PVT is not that easy to manufacture, so you need to be skilled in thermal engineering too to provide good product and have no delamination problem. And the first prototypes PV manufacturer did was maybe not as good as what we can do now in the PVT manufacturer market.
Okay.
Maybe another explanation. I can add something verbal. The PVT,
yes, sure.
the PV manufacturers are mainly Chinese, as we know, and the Chinese market with flat plate collectors is not that developed. It's mostly evacuated tube, and it's a completely different approach, and it's very difficult to get to a PVT with evacuated tube. We have a good example in Europe. We showed a few slides on that. But if you combine the two in China, I think it's difficult for both of them. So PVT is a European style thing for the moment, and as soon as we get more PV producers in Europe, which I think we will have after what we have been passing through, I'm sure we get more PVT manufacturers or people interested into PVT products.
Well, apropos, our audience today looks rather also coming from outside Europe, and they are looking into examples in the Middle East, was one participant asking for, or asking for experiences and simulations in hotter climates and what will happen to the PVT cool down effects. Does anybody of you has looked into these more, well, hotter regions?
Well, we have in Task 60, we have someone coming from Australia, and he is very keen on that because he has the climate that you were mentioning. Certainly, there is more cooling effect in those latitudes, Middle Asia, than or Middle East. There is a cooling effect, certainly, but I don't want to have it like a main argument. You know, it's what I said previously, but of course, the hotter the climate, the better it is to go with PVT, because you're going to probably limit the temperature to what the domestic hot water is asking if you do something for the building, like 45, 50 degrees Celsius, and not up to 80 or even a little bit more, 80 degrees Celsius. That you can see this on PV modules in Abu Dhabi or Dubai. So it's a good thing to. When what I said, if you think PV, before doing the installation, think PVT and do the calculation.
Absolutely, yes. Well, maybe one of the last questions here, and somebody wants to know, is there any interlink to the grid if you do the PV side grid integrated or feeding into the grid? Does it affect the PV performance or PVT performance in any way?
I guess Laetitia can have the word on this also, but of course not. PV is exactly the same in PVT than in PV. But the more you use it as a self-consumption, if the electricity you pay is, say, 20 cents, and the grid is buying at 8 cents, you better off use this electricity yourself. It's exactly the same case than with PV. Laetitia, maybe you can add something.
Yeah, you're totally right. Most of our installation are grid connected. Even if you self-consume the majority, you can sell in the grid the surplus, and it is exactly the same as PV.
One thing more maybe on this, Bebel, the more electrical cars we're going to have, the more battery capacity we will have, and maybe the more PVT will be installed, because you can use this also for your car, and you produce heat for your pool, for your domestic hot water, for your space heating, and you use the surplus for your car. So when you think PV for your car, think PVT first.
Well, yes. Another question regarding testing and standards. Is there already a specific PVT standard in place or in effect or under development?
Yeah, that's what I tried to explain. With the solar Kemal label, it was explained what to do with norm. We use the photovoltaic norm, the IEC norm. 61 to 15 and 61 730 for the photovoltaic part, and for the thermal part we use the classical ISO 9806, which has a dedicated part for PVT testing, but for the thermal part. But it's really important that the old PVT has to repass the IEC, the PV IEC, because the PV design is maybe has to be integrated in the PVT. So the fixation, the glue, or anything you add in your PV means that you need to repass the IEC certification.
Okay, thank you. Oh, well, I thank all the participants for their many questions. I hope I have got the most important ones. Sorry for not being able to really address all of them. I thank the speakers for their really comprehensive and interesting way of presenting. Thanks to all the participants for their questions, and I wish you all a nice afternoon and another healthy several weeks. And I hand over to Arabella.
Yes, thank you very much, Bärbel, for the moderation, and of course, thank you very much to our speakers for the presentations. I think after those passionate talks, we are now, everybody is for sure on top of considering PVT the next time they ever have to consider anything. So thank you very much for the talks. We received many questions and we got through quite a lot of them, so I'm quite happy with that, and I hope your question got addressed as well. We also got many questions regarding the webinar recording and the presentation. So the recording as well as the presentations, they will be available on both the ISES as well as the IEA SHC Solar Academy homepage in the next few days. So that's coming up soon for you to rewatch. For our ISES members on the webinar today, remember you already have the unlimited access to all ISES past webinars and presentations in our webinar archive. So just go over there and log in and you will have full access to all of our resources. And then again, thank you very much for everybody attending today. And we of course appreciate your participation and also your feedback. You will receive a little survey at the end of the webinar in an email. So we would be very happy for you to consider that survey. You can always write to us at public.relations@ises.org, and you can find us on all the social media channels as well. So just reach out to us there as well and join us in the solar community. And with this, I think we're going to end for today. Thank you very much. And as Bärbel said, stay safe, stay healthy, and we will be back with another webinar very soon. So tune back in and have a good day. Bye-bye.